All right, so in this one, we're still doing a volume of a solid, but we're going to have two different curves, and we're going to actually rotate it around the x-axis and then around the y-axis. So this will be interesting. We'll see if we can get through it. So here are our curves. Y equals e to the x over 3 minus 1, like that. And y equals arc tan of x. Cool. So the region enclosed by those curves, there's only one region enclosed by those curves. So it looks like the only region enclosed is this little zone, this little sliver right here. Okay? So if we rotate that around the x-axis, let's do the x-axis first. One way to help visualize what's going on is to just copy those same equations down and multiply them by -1. Because multiplying it by -1 will just flip it around. So this is going to help me and help you just sort of see what the other thing is. And then, of course, we're rotating it out of the computer screen. So we're rotating it 360 degrees, 2 pi radians around. And so it's making this sort of open-ended bowl. So you've got an outer radius here connecting the arctan to the arctan. And then you've got like an inner radius here connecting the e to the x to the other e to the x. And so I want you to think back to when we found the area in between two curves. We did the higher curve minus the lower curve because those integrals will then leave me with the in-between area. And here we're going to do the same idea. We're going to do the volume of the outer shape minus the volume of the inner shape. So the volume around x, let's just call that Vx, would be, well, we can find the points of intersection. You're not going to really be able to find those points of intersection by hand because, well, one of them is just 0. That's not so bad. But then the other one, I don't think that there's a nice way to find that. So we got 2.314. So we're going to do the volume from 0 to 2.314. Everything's going to have a pi in it. We're going to do pi times the big radius squared minus pi times the little radius squared. So I'm just going to put a pi in front of it all. The big radius is the outer function. The outer function looks like arctan. So we're going to do arc tan of x squared. And then the inner function is the e to the x over 3 minus 1 squared dx. Tell you the truth, I don't know if this is something that you can integrate by hand. You can definitely get the integral using a calculator. Desmos can handle that. If I just type in pi, and then to get an integral, you just type int. And as soon as you hit dx at the end, oh, oh, why is that not working? It says integrand must end with an integration variable like dx. I think I did that. Interesting. Let's try it in, maybe if I try it in two different integrals. It's interesting. I don't know why it was, I don't know what little formatting issue I was having there. seems to work. So you could just subtract those two values to get the integral as it rotates, the volume as it rotates around the x-axis. The reason why I'm saying that I don't think I could do it by hand is both of these pieces are pretty nasty. So if you look at like arctan of x squared, there's no u substitution that's going to work because its derivative doesn't show up anywhere else. I could do try to do like integration by parts, where I would say something like u equals arctan of x squared, and then dv equals dx, and this might work out. V equals x. The thing I'm worried about is my du, 2 arctan of x, and then what is the derivative of arctan? I think the derivative of arctan is just 1 over, I think it's just 1 over 1 plus x squared. And then I'd have to do like another integration by parts. So that's going to get pretty nasty. And so that one would be hard to do. This first part would be hard to do by hand. And I think the second part would be hard to do by hand also, because I can't do a u substitution. If I tried to like square it out, I would have the first piece squared minus 2 times the first piece plus the second piece squared. This I can integrate. This I can integrate. The first piece I can't integrate. E to the x squared over 9 is not something that I'm able to integrate. I, again, would try to do integration by parts, but that's just going to result in another e to the x squared over 9. So I think the only way to do that is by using technology. Anyway, let me finish up with I'll expect to use technology around as we rotate it around the y-axis. So as we rotate it around the y-axis, what I'm going to have to do is switch each of those functions around. So for this one, we just know that's going to be tan of y equals x. For this one, we're going to do y plus 1, and then we're going to natural log that, and then we're going to multiply that by 3 to get x. And when we did the rotation around the x-axis, we did the outer minus the inner. So now we're having the y-axis as our center, still further minus closer. So it's the right function minus the left function. And so this function on top is on the right, and this function on bottom is on the left. And so our Vy, our volume y, is going to be, one other piece I need is I need that point of intersection. I need the y value, 1.163. So 0 to 1.163. The function on the right squared minus the function on the left squared dy. And so that'll pop out. I hope I can type it all in at one time this time. Pi integral 0 to 1.163, 3 natural log y, come on, plus 1 squared minus tan y squared dy. God, I don't know why it's giving me that error. That's annoying. So yeah, it's really annoying. It's making me split it into 2 chunks. Then you would, yeah, add those together because I have a negative in the expression, or subtract those two values there. So that's the process. I always feel a little bit unsatisfied when I have to just say, okay, you got to do it by technology. But part of the work was getting the setup and recognizing how to switch the functions around in terms of x and y. So anyway, thanks for watching. Ask questions and let me know how I can help.